3, 2, 1. Okay, what's happening, everybody? Welcome back to the part 2 of the section 4. It's 4.2 now, section 4.2 video. In the very first video, or the video I filmed with the class, the Wi-Fi went out, so that recording is, what's the PC word for crap? It's not good. So anyway, I'm going to record a second bit just for you viewers at home, right here with the rest of the class. So let's get going. So the last thing we just did is we proved that the rational numbers are not closed under division. Yes, that's what we did. It's so much weirder without a class here to like interact with. But anyway, we got this. It's okay. I don't need anyone. I can math all alone. So that was the last thing we did. But really, the reason why the rational numbers weren't closed under division was just 0. 0 was the only kind of problem child here, right? Because the issue was that if you take any rational number and divide it by 0, you're going to get something undefined. And undefined is not a rational number, right? It's just literally nothing. It's undefined. It doesn't mean anything. So the thing is, though, what if we just take out 0? So let's first make a definition. So let's see here. I think I used purple. You know what? I'll just follow what I did in class. Here we go. So definition. There's 2 I's. Well, I have 3 I's. Oh my God, it's a lot of I's in definition. There we go. Definition. Q with a star is meant to denote the set of all the rational numbers except 0. So exactly the set we're talking about. Just set of rational numbers, take out 0, take out that problem child, it'll be good. So the way you can write this is you can say Q star is all the x that are rationals, so x in the rational numbers, such that x does not equal 0. That's literally how you read this set notation. We'll go through it more in depth, like chapter 6 or some crap like that. But see, now I'm saying the word crap. Now I feel so open and free because there's no one here to call me on it. But anyway, yes. So yeah, crap. The word crap is me being free. Yes. So the point is, this is Q star, all the rational numbers, not 0. And so I'm going to write this. This is all non-zero rational numbers. And I want a curly bracket there, not a parentheses. There we go. Then we're going to line it up. So let's get excited. Let's do it. So the point is, yeah, we have the definition here. Why do I want to bring this up? Well, I want it's cool. Right? And the star thing applies to more than just the rational numbers. We call Z star the set of integers without 0. R asterisk, I guess, the set of real numbers without 0. So it's a common notation. Means that it comes up. But specifically, here's the question. If it is true that the only reason the rationals aren't closed under division is because it's 0, what happens if we just simply take out 0? So here's the claim. Q star is closed under division. Ooh. And so Q star is closed under division. What's that mean formally again? What's that actually mean? And I hope, by the way, that we're getting comfortable enough with like quantifiers for all and there exists, that when I say what does the thing mean, it actually helps us see it in quantifiers to really solidify what this concept is saying. Whereas before, it might have helped to see it in English. I hope quantifiers you realize are actually more useful sometimes because they're more concrete, not up for interpretation, really. So the 4 ways to say this is being closed under any operation means that if you take any 2 elements in the set and you put them through the operation, it'll stay in that set. You can't get out of the set by doing that operation. So what I mean is that for all x in Q star and, for all x in Q, let's not ruin the board here. There you go. For all x in Q star, for all y in Q star, x over y, division stays in Q star. Let's just go ahead and see First of all, if we think this is true, right, let's make an aside here, right? Because the first thing we always do before we prove something is decide what we're trying to prove and why we think is true, right? We need like a proof sketch, like an idea of what we're going to do. So the idea here is if we take any x over y, if x and y are both rational numbers, that rather than q star, that means that they're rational numbers that aren't zero. So in particular, x can be written as a over b, and y can be written as c over d, where a, b, c, and d are all integers, and then b does not equal 0, and d does not equal 0. That's what it means to be rational. Okay, so then we know we can divide rationals by flipping and multiplying. So we get d multiply, this is the same as a over b times d over c. And then by fractional multiplication, we get this. So here's the question. Is this in Q star? And here's the time in class where I normally wait for a very long time for someone to muster up the courage to answer. But I don't do that anymore because I know the answer and I have plenty of courage. So the point is, this is unbelievable. So that's what the cowardly lion trying to prove he's cured. I have courage, don't worry about me. I don't need help. Yes, this is AD over BC. The question is it in Q star? And well, what's it mean to be in Q star? That means it's a rational number that's not zero. Well, let's think about this, right? Note, can it be zero? First of all, we can do this in any order. I'm just going to start with the zero part. Can this be zero? Note if AD over BC equals 0, that would imply what? That implies AD equals 0, right? If a fraction is 0, the top must be 0. It's got to be, just if you think about it. And then, yeah, and so if AD equals 0, what that implies is that A equals 0 or D equals 0. Right? That's just how this rolls. The zero product property. What it means is that for anything called fields in math, it's a whole thing of which the rational numbers are one of them. If two numbers multiplied be 0, that means at least one from 0. Pretty interesting. The point is we have this property. So A equals 0 or D equals 0. But the problem is, remember, right, that A over B and C over D equal X over Y are in Q star. So if A equals 0, that means A over B, which is X, would equal 0. But X is specifically a non-zero rational number, so it can't be 0. So this couldn't happen. And same thing with D. Actually, D is a little different. D can't be 0 because it's the denominator of a rational number. So by definition, it can't be 0. So we knew that one wasn't 0 already. So that also can't be 0. So AD doesn't equal 0. So the whole thing's not 0. So thus, AD over BC is not equal to 0. Since if it did, that would mean AD equals 0, which means A equals 0, B equals 0, or D equals 0, and both of those can't happen. Okay, so we know it's non-zero, but it's a rational. If it is, if it's a non-zero rational, and then we've kind of shown, okay, it actually is, or the non-zero rationals actually are closed under division. So let's get into it. Well, to be a rational number, all that means is that you're a ratio of integers. Well, heck, this looks like a ratio, right? You have an AD over a BC. The question is, are those integers? Well, this is just multiplication of two integers, right? Multiplication of two ends. So, ends. And same thing here. Multiplication of two ends. So, integer, right? So we just so what all this means is that yeah, this is in fact a rational number. This is the ratio of two integers. Whenever you multiply integers together, you get integers. And since we know A, B, C, D are integers by the definition of rational numbers, where these things come from, A times D, B times C will be integers. So this is a ratio of integers, and we're good. The only little subtle thing we have to show here is that remember that rational numbers are ratios of integers where the bottom can't be 0. The denominator must be non-zero. And is BC equal to 0? Well, remember if BC equals 0, that would imply B equals 0 or C equals 0, which for similar arguments above can't happen. So BC can't be 0. Okay, so BC can't be 0. meaning that AD over BC, which equals X over Y, is in fact a ratio of integers that's non-zero, meaning it's a rational number that's non-zero, so it's in the non-zero rationals. We're talking in circles here. The point is, yes, this looks like it should be closed under division. Okay, my hair is crazy right now, but the point is, and it reflects my inner, my hair reflects my inside. But the point is my emotional state. But what's the point? Oh yeah, so the point is, this looks like the claim will be true. I say looks like only because we haven't really proven it yet. This is all kind of informal. The whole point of a proof is that we're going to sit down and write down every single detail, make sure there's nothing we missed. All right? If you do a proof correctly, if you do a proof, this sounds stupid. I was going to say if you do a proof correctly, there's no way you can be wrong. But what I mean by that is that if you lay out a proof, you don't skip any steps, you do everything validly, that's a word, right? Then your conclusion must be true, and we can be sure that we're right. I mean, as sure as we are, yeah, I'm just gonna leave it there. I mean, technically, I mean, I guess someone could skip like maybe like you could like overlook a detail in a proof. You don't even know it's like you just kind of forget about it, and then I guess there's a probability that every other human being that looks at it forgets about it. But assuming that human beings, assuming that human beings aren't being deceived by our own brains, then we can be sure. That's really as sure as you can be, right? Forget that part. It doesn't mean anything. The point is, if the proof is valid, we can be sure in our conclusions.